Introduction to MGF1. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're going to talk about MGF1, which stands for Mask Generation Function 1. This is a really interesting cryptographic building block that you might not have heard of, but it is used extensively in modern security systems. MGF1 is like a magical machine that takes a small amount of random data and stretches it into a much larger amount of pseudo-random data. Think of it like taking a tiny seed and growing it into a big tree of randomness. The best way to understand MGF1 is through a simple analogy. Imagine you have a small bottle of concentrated food coloring, just a few drops. But you need to color a whole swimming pool of water. You can't just pour in those few drops and expect the whole pool to turn color evenly. MGF1 is like a process that takes those few drops and carefully distributes them throughout the entire pool, creating consistent color everywhere. In cryptography, instead of food coloring and water, we're working with random numbers and pseudo-random masks. MGF1 was standardized as part of PKCS number 1, which is the RSA cryptography standard. It is defined in RFC 8017 in Appendix B.2. The function is used primarily in RSA ESOAEP padding, which is the secure way to use RSA encryption. However, the concept is simple enough that we can understand it without diving deep into RSA or OAEP. The key thing to understand is that MGF1 solves a practical problem. How do you turn a short random value into a long pseudo-random value in a way that is secure and verifiable? The problem MGF1 solves. Let's start by understanding what problem MGF1 was designed to solve. In cryptography, we often need random data. Random data is used for encryption keys, initialization vectors, random seeds, and padding. The challenge is that generating truly random data is expensive and slow. Your computer has to gather entropy from various sources like mouse movements, keyboard timings, network packet timings, and hardware noise. This process takes time and you can only generate random data at a limited rate. Now imagine you're building a security system and you have a small amount of truly random data, let's say 32 bytes. But your system needs 200 bytes of random-looking data for a particular operation. You can't just repeat your 32 bytes over and over because that would create patterns. If you took your 32 bytes and repeated them, an attacker could notice this repetition and potentially exploit it. You also can't just pad with zeros because zeros aren't random at all. What you need is a way to expand or stretch your small random seed into a larger pseudo-random output. The output doesn't need to be truly random in the same way the seed is, but it needs to look random to anyone who doesn't know the seed. It should be unpredictable, have no obvious patterns, and be evenly distributed. This is exactly what MGF1 does. It takes your short seed and expands it into a longer mask that appears random. Another important requirement is that the process must be deterministic. This means that if you put in the same seed, you must always get the same output. Why is this important? Because in cryptographic protocols, both the sender and receiver need to be able to compute the same masks independently. If the mask generation was truly random, they could never synchronize. By being deterministic, MGF1 ensures that anyone with the same seed can generate the same mask, but without the seed, the mask appears completely random. How MGF1 works. The basic idea. The fundamental idea behind MGF1 is beautifully simple. It uses a hash function like SHA-256 as its core component. A hash function is like a one-way scrambling machine. You put data in, and it produces a fixed size output that looks completely random. For SHA-256, the output is always exactly 32 bytes, no matter how much data you put in. The hash function has the property that even a tiny change in the input produces a completely different output. Here's how MGF1 uses the hash function to generate a long mask from a short seed. First, you take your seed and hash it along with a counter starting at 0. This gives you the first 32 bytes of your mask. Then, you increment the counter to 1, hash the seed plus counter again, and get another 32 bytes. You keep doing this, incrementing the counter each time, until you have generated enough bytes. Finally, you trim the result to exactly the length you need. Let's make this concrete with an example. Suppose your seed is the word hello and you need 70 bytes of mask. Using SHA-256, you would compute hash of hello plus 0, which gives you 32 bytes. Then hash of hello plus 1, giving you another 32 bytes. Then hash of hello plus 2, giving you another 32 bytes. That's 96 bytes total. Since you only need 70 bytes, you take the first 70 bytes and discard the rest. The counter is typically encoded as a 4-byte number in Big Endian format. The brilliant thing about this approach is that each hash operation produces output that looks completely random and unrelated to any other hash output. Even though all these hashes use the same seed, the counter changes each time. This means the hash inputs are all different, and consequently, the outputs are also different and uncorrelated. This gives you a long stream of pseudo-random bytes that appears to have no patterns or structure. MGF1 algorithm step by step. Let us walk through the MGF1 algorithm in detail, with exact steps, so you can see precisely what happens. The algorithm takes 3 inputs. First, the seed, which is the short random data. Second, the desired mask length, in bytes. And third, the hash function to use, typically SHA-256. The algorithm produces one output, a mask of the exact length that was requested. Step 1 is initialization. You create an empty output buffer where you will accumulate your mask bytes. You set a counter variable to 0. You also need to know the hash length, which is how many bytes your hash function produces. For SHA-256, this is 32 bytes. For SHA-512, it would be 64 bytes. Step 2 is the main generation loop. You check if your output buffer has enough bytes yet. If not, you continue with the loop. You take the counter value and convert it to a 4-byte representation. In hexadecimal, counter 0 becomes 0x, beginning with 00, ending with 00. Counter 1 becomes 0x, beginning with 00, ending with 01, and so on. You concatenate your seed with these 4 counter bytes. Then you hash this combined data using your hash function. You append the resulting hash output to your output buffer. Then you increment the counter by 1. Step 3 is determining when to stop. After each iteration, you check if your output buffer length is greater than or equal to your desired mask length. If it is, you exit the loop. If not, you continue with another iteration. The number of iterations you need is the ceiling of desired length divided by hash length. For example, if you need 100 bytes and your hash produces 32 bytes each time, you need ceiling of 100 divided by 32, which is 4 iterations. Step 4 involves the final truncation. Your output buffer now contains at least the number of bytes you need, though probably a few extra. You simply take the first n bytes from your buffer, where n is your desired mask length, and discard the rest. This truncated result then becomes your final mask. The algorithm is now complete, and you can return this mask. Concrete example with real numbers. Let's work through a complete example with actual numbers so you can see MGF1 in action. Imagine we have a seed that is 32 bytes of data, and for simplicity let's say our seed is just 32 zeros in hexadecimal. 0x, beginning with 00 ending with 00. In reality, this would be random data, but using zeros makes the example clearer. We want to generate a mask that is 100 bytes long using SHA-256. First, we calculate how many hash operations we need. SHA-256 produces 32 bytes per hash. To get 100 bytes, we need the ceiling of 100 divided by 32, which equals 4 iterations. So we'll perform 4 hash operations and then truncate to 100 bytes. Iteration 1. We concatenate our seed with counter beginning with 0x00 ending with 00. This gives us a 36-byte input to SHA-256. The hash of this input produces our first 32 bytes of output. Let's call this output block H0. Iteration 2. We concatenate our seed with counter beginning with 0x00 ending with 01. This gives us a different 36-byte input. The hash produces another 32 bytes. Let's call this H1. Iteration 3. We use counter beginning with 0x00 ending with 02, hash it with the seed, and get another 32 bytes H2. Iteration 4. We use counter beginning with 0x00 ending with 03, hash it with the seed, and get the final 32 bytes H3. Now, we have 4 hash outputs, H0, H1, H2, and H3, which is 128 bytes total. We concatenate them to form a 128-byte sequence. As we only need 100 bytes, we take the first 100 bytes and then discard the final 28 bytes. These 100 bytes form our MGF1 output mask. The important thing to notice is that even though our seed was all zeros, the output mask does not have any obvious pattern. Each of the 4 hash outputs looks completely random and unrelated to the others. This is because even tiny changes in the hash input produce completely different outputs. The counter values 0, 1, 2, and 3 are enough to make each hash completely different. If we ran MGF1 again with the exact same seed and requested the same 100-byte length, we would get the exact same output. But if we changed even one bit of the seed, the entire output would be completely different. Why hash functions make MGF1 secure? The security of MGF1 entirely depends on the properties of the hash function being used. A cryptographic hash function has several important properties that make MGF1 work securely. Let's explore each of these properties and understand why they matter. The first property is called pre-image resistance. This means that given a hash output, it is computationally infeasible to find an input that produces that output. In other words, hash functions only work in one direction. You can easily compute the hash of some data, but you cannot reverse the process. For MGF1, this means that even if an attacker sees the mask output, they cannot work backwards to figure out what seed was used. This is crucial because in many cryptographic systems, the seed needs to remain secret. The second property is collision resistance. This means it is computationally infeasible to find 2 different inputs that produce the same hash output. While this property is less directly relevant to MGF1's security, it contributes to the overall unpredictability of the output. It ensures that different seeds will almost certainly produce different masks. The third property is the avalanche effect. This means that a small change in the input produces a large change in the output. If you change just one bit of the input, on average about half the bits in the output will change. For MGF1, this is what makes each iteration produce completely different output even though the counter only changes by 1. Going from counter 0 to counter 1 flips just one bit in the input, but the hash outputs are completely uncorrelated. The fourth property is that the output appears random and uniformly distributed. Good hash functions produce output where every bit has about a 50% chance of being 0 or 1, and the bits are independent of each other. There are no patterns or correlations in the output. This is why MGF1's output can serve as a pseudo-random mask. Even though the process is deterministic and reproducible, to someone who doesn't know the seed, the output looks like truly random data. These properties together ensure that MGF1 can safely expand a short random seed into a long pseudo-random mask without compromising security. MGF1 in RSAESOAEP. Now let's look at how MGF1 is actually used in practice, specifically in RSA-SOAEP, which is the secure padding scheme for RSA encryption. Understanding this real-world application helps clarify why MGF1 was designed the way it was and why the expansion property is so important. In OAEP, we need to encrypt a message using RSA. The message is combined with a random seed through a clever padding scheme. The padding scheme has two main components. First, a random seed that is relatively short, typically 32 bytes when using SHA-256. Second, a data block that contains the message along with some padding, which might be several hundred bytes long depending on the RSA key size. The security of OAEP comes from cross-coupling these two components using MGF1. Here's how it works. First, we call MGF1 with the random seed as input and request an output length equal to the data block size. This might be 200 bytes or more. This gives us dbmask, which is a pseudo-random mask the same size as the data block. We XOR the data block with dbmask to create masked dbXOR, which stands for exclusive OR, is a bitwise operation where each bit of the data block gets flipped or not flipped based on the corresponding bit in the mask. Then we do something clever. We call MGF1 again, but this time, we use masked db as the seed, and request an output length equal to the original random seed size, which is 32 bytes. This gives us the seed mask. We XOR the original random seed with the seed mask to create the masked seed. The result is that both the data block and the seed are masked. And they are masked in a way that depends on each other. This cross-coupling is what provides the security. Why do we need MGF1 for this? The key reason is size mismatch. The random seed is only 32 bytes, but the data block might be 200 bytes. We cannot just XOR them directly because they are different sizes. MGF1 solves this by expanding the 32-byte seed into a 200-byte mask. Similarly, we have a 200-byte masked DB but need a 32-byte mask for the seed. So we use MGF1 to generate a 32-byte mask from the 200-byte value. MGF1 provides the flexibility to generate masks of any size from seeds of any size, which is exactly what OAEP needs. Different hash functions with MGF1. MGF1 is designed to work with any cryptographic hash function, and the choice of hash function affects both the security and performance of the mask generation. Let's explore the different hash functions commonly used with MGF1 and understand the trade-offs involved. SHA-256 is the most common choice for MGF1 today. SHA-256 produces 32-byte outputs and is considered secure against all known attacks. When you use SHA-256 with MGF1, each iteration gives you 32 bytes of mask. If you need a 100-byte mask, you need 4 iterations. The security level of SHA-256 is considered to be 128 bits, which means an attacker would need to perform about 2 to the power of 128 operations to break it. This is astronomically large and completely infeasible with current or foreseeable technology. SHA-384 and SHA-512 are alternatives that produce longer outputs. SHA-384 produces 48-byte outputs, and SHA-512 produces 64-byte outputs. The advantage is that you need fewer iterations to generate a long mask. For a 100-byte mask with SHA-512, you only need 2 iterations instead of 4. The disadvantage is that each hash operation is slightly more computationally expensive. SHA-512 is particularly interesting because on 64-bit processors it can actually be faster than SHA-256 in some implementations, even though it produces more output. You might wonder about SHA-1, which was a predecessor to SHA-256. SHA-1 produces 20-byte outputs and was widely used in the past. However, SHA-1 has known collision vulnerabilities discovered by researchers. While these vulnerabilities don't directly break MGF1's security model, the cryptographic community recommends against using SHA-1 for any new systems. If you're implementing MGF1 today, you should use SHA-256 or stronger. The choice of hash function is specified as a parameter to MGF1, which makes the function flexible and future-proof. If a new, better hash function is developed in the future, MGF1 can simply use that function without changing the overall algorithm structure. This design principle of separating the mask generation logic from the underlying hash function is an example of good cryptographic engineering. MGF1 properties and characteristics. Let's examine the important properties and characteristics of MGF1 that make it suitable for cryptographic applications. Understanding these properties helps explain why MGF1 is designed the way it is and why it is trusted for security-critical operations. First, MGF1 is deterministic. Given the same seed and requested length, it always produces exactly the same output. This determinism is essential for cryptographic protocols where both parties need to independently compute the same mask. In OAEP, both the encryptor and decryptor need to be able to generate the same masks, so determinism is required. However, to an observer who doesn't know the seed, the output appears random. Second, MGF1 provides pseudo-randomness. The output passes statistical randomness tests and has no detectable patterns or correlations. Each byte of output appears independent and uniformly distributed. This property comes from the hash function's properties. As long as the seed is truly random, the MGF1 output will be pseudo-random and suitable for use as a cryptographic mask. Third, MGF1 is computationally efficient. The algorithm is simple and only requires hash function operations, which modern processors can perform very quickly. For a 100-byte mask using SHA-256, you need only 4 hash operations. On a modern computer, this takes microseconds. The efficiency comes from the fact that we are not doing any complex mathematical operations beyond hashing and concatenation. Fourth, MGF1 has variable output length. You can request any length of output from 1 byte to extremely large sizes limited only by the counter size. The counter is 4 bytes, so theoretically you could generate up to hash length times 2 to the power of 32 bytes of output, which is far more than any practical application would ever need. This flexibility is valuable because different cryptographic operations need different length masks. Fifth, MGF1 is one-way. Given the mask output, it is computationally infeasible to determine what seed was used to generate it, assuming the hash function is secure. This property inherits from the pre-image resistance of the hash function. Even if an attacker intercepts or observes the mask, they cannot work backwards to discover the secret seed. This is important for the security of systems like OAEP where the seed must remain confidential. Implementing MGF1 in Python. Let's look at how to implement MGF1 in Python so you can see the algorithm translated into actual code. Python is a great language for demonstrating cryptographic concepts because the code is readable and there are excellent cryptographic libraries available. We'll build a complete, working implementation that you can run and experiment with. First, we need to import the necessary libraries. We will use the hashlab library, which provides cryptographic hash functions, including SHA-256. We will also use struct for converting integers into bytes. Both of these are part of Python's standard library, so you do not need to install anything extra. The main function takes 3 parameters: the seed as bytes, the desired mask length as an integer, and the hash function to use, which defaults to SHA-256. Inside the function, we first initialize an empty bytes object to accumulate our output. We set a counter to 0. We also determine how many bytes each hash operation produces. To do this, we call the hash function on an empty input and measure the result length. Then, we enter a loop that continues until our output length reaches the desired mask length. Within each iteration, We convert the counter into a 4-byte big endian representation using struct.pack. We then concatenate the seed with the counter bytes, hash this combined data using the specified hash function, append the resulting hash digest to our output, and increment the counter. After the loop completes, we have generated at least as many bytes as requested. We truncate the output to exactly the requested length by slicing the bytes object. Finally, we return this truncated output as our mask. The entire implementation is only about 20 lines of code, which shows how simple the algorithm is. To use this function, you would call it like this: mask equals MGF1, with arguments such as your seed bytes, the desired length like 100, and optionally specifying a hash function. The function returns a bytes object containing your pseudo-random mask. You can then use this mask for XOR operations, or whatever your cryptographic protocol requires. This implementation is instructional and shows the algorithm clearly, but for production use, you would want to use a well-tested cryptographic library that includes MGF1 rather than implementing it yourself. MGF1 in OpenSSL and cryptographic libraries. MGF1 is implemented in virtually all major cryptographic libraries because it is an essential component of RSAESOAEP. Understanding how different libraries implement and expose MGF1 helps you use it correctly in your applications. OpenSSL is probably the most widely used cryptographic library in the world, and it has a complete implementation of MGF1 that has been thoroughly tested and audited. In OpenSSL, MGF1 is not typically called directly by application developers. Instead, it is used internally when you specify OAEP padding for RSA operations. When you use the EVP interface in OpenSSL and configure it for OAEP padding, OpenSSL automatically uses MGF1 behind the scenes with the hash function you specify. However, if you are implementing custom cryptographic schemes or need MGF1 for other purposes, OpenSSL does provide functions to call MGF1 directly. The OpenSSL function for MGF1 is called PKCS1MGF1. This function is part of the RSA implementation and is declared in the OpenSSL/RSA.h header file. The function takes a seed buffer, a seed length, an output buffer, an output length, and a message digest context that specifies which hash function to use. The function fills the output buffer with the generated mask. You need to pre-allocate the output buffer to the desired size before calling the function. Other cryptographic libraries have similar implementations. Python's cryptography library exposes MGF1 through the padding module. In Java, the Bouncy Castle library provides MGF1 as part of its RSA implementation. The .NET framework includes MGF1 in its system.security.cryptography namespace. All these implementations follow the same algorithm specified in RFC 8017, ensuring interoperability. If you generate a mask with OpenSSL's MGF1 using a particular seed and hash function, you will get the exact same result from Python's cryptography library or any other standards-compliant implementation. This consistency is crucial for cryptographic protocols where different parties using different libraries need to compute the same masks. Security analysis of MGF1. Let's examine the security properties of MGF1 in detail to understand why it's considered secure for cryptographic applications. The security of MGF1 is analyzed in the context of the random oracle model, which is a theoretical framework used in cryptographic proofs. In this model, hash functions are assumed to behave like truly random functions, meaning their outputs are completely unpredictable and uniformly distributed. Under the random oracle assumption, MGF1 is provably secure for its intended purpose of generating pseudo-random masks. The key security property is indistinguishability from random. This means that if you give an adversary two masks, one generated by MGF1 from a random seed, and one that is truly random, the adversary cannot distinguish which is which with better than random guessing probability. This property holds even if the adversary can generate many masks using different seeds of their choice. Another important security consideration is resistance to seed recovery. Given a mask output from MGF1, it should be computationally infeasible for an attacker to determine what seed was used to generate it. This property comes directly from the pre-image resistance of the underlying hash function. Breaking this would require either finding a pre-image for one of the hash outputs or somehow reversing the counter concatenation and hashing process, both of which are considered computationally infeasible for good hash functions like SHA-256. However, it is crucial to understand that MGF1's security depends entirely on two things: the security of the underlying hash function and the randomness of the seed. If the hash function is broken, for example if collision attacks become practical, then MGF1's security guarantees may be compromised. This is why using deprecated hash functions like SHA1 with MGF1 is dangerous. Similarly, if the seed is not truly random or is predictable in any way, then the MGF1 output becomes predictable as well. The security of the entire system is only as strong as its weakest component. There is also a practical consideration. MGF1 assumes the counter does not overflow. With a 4-byte counter, you can generate up to 2 to the power of 32 iterations before overflow, which with SHA-256 gives you 137 gigabytes of mask. This is far more than any practical application needs, so overflow is not a real-world concern. Performance characteristics and optimization. Understanding the performance characteristics of MGF1 is important for system design, especially when processing many cryptographic operations per second. The performance of MGF1 is dominated by the cost of hash function operations. Each iteration requires one hash computation. So, for example, if you need a 200-byte mask with SHA-256, you need 7 hash operations. The speed of MGF1 therefore directly depends on how fast your system can compute hashes. Modern processors have become very efficient at computing cryptographic hashes. Intel and AMD processors have special instructions called SHA extensions that accelerate SHA-256 computations. On a modern processor with these extensions, you can compute millions of SHA-256 hashes per second. This means MGF1 is extremely fast for typical mask sizes. Generating a 200-byte mask might take only a few microseconds on modern hardware. For most applications, MGF1 performance is not a bottleneck. However, there are scenarios where MGF1 performance matters. In high-throughput systems processing thousands of RSA-OAEP encryptions per second, the MGF1 operations can become significant. Each OAEP encryption requires 2 MGF1 calls, so optimizing these operations provides real benefits. There are several optimization strategies you can employ. First, choose an efficient hash function implementation. Hardware-accelerated implementations are much faster than software-only implementations. Second, consider the hash function choice. SHA-512 might seem slower than SHA-256, but on 64-bit processors, SHA-512 can actually be faster per byte of output because it processes data in 64-bit chunks and produces 64 bytes per iteration instead of 32. Another optimization is batch processing. If you are generating many masks, you might be able to structure your code to take advantage of CPU pipelining and cache locality. However, be extremely careful with optimizations that might compromise security. For example, you might be tempted to cache MGF1 outputs to avoid recomputation, but this could introduce timing side channels or memory disclosure vulnerabilities. Any optimization must be carefully analyzed to ensure it does not weaken security. In practice, the best approach is to use well-optimized cryptographic libraries like OpenSSL that have already implemented and tested efficient MGF1 code. These libraries balance performance with security and are maintained by experts who understand the subtle security implications of implementation choices. Test vectors and validation. Test vectors are essential tools for validating that your MGF1 implementation is correct. A test vector is a set of known inputs and the corresponding expected outputs. By running your implementation with the test vector inputs and comparing your results to the expected outputs, you can verify that your code is working correctly. RFC 8017 includes comprehensive test vectors for MGF1 in Appendix B. Let's look at a simple example test vector. Suppose we have a seed that is the ASCII text foo, which is 3 bytes, 0x66, 0x6f, 0x6f in hexadecimal. We want to generate a 50-byte mask using SHA-256. The test vector would specify the exact hexadecimal bytes that should result from this operation. When you run your MGF1 implementation with this seed and length, you should get exactly those bytes. If even 1 byte is different, there is a bug in your implementation. Test vectors are particularly important for MGF1 because small implementation errors can produce outputs that look correct but are actually wrong. For example, if you accidentally use little endian instead of big endian encoding for the counter, you will still get output that looks random, but it will not match the standard. Or if you forget to truncate at the exact requested length and instead round up to a multiple of the hash length, you will generate masks that are too long. These kinds of errors can cause interoperability problems where your encrypted data cannot be decrypted by standard compliant implementations. When implementing or testing MGF1, you should verify it against multiple test vectors that cover different scenarios. Test with different seed lengths, ranging from very short, like 1 byte, to longer lengths, like 64 bytes. Test with different requested mask lengths. This includes lengths shorter than 1 hash output, lengths exactly equal to 1 hash output, slightly longer lengths requiring 2 iterations, and much longer lengths requiring many iterations. Test with different hash functions, including SHA-256, SHA-384, and SHA-512. By thoroughly testing against known vectors, you can have confidence that your implementation correctly follows the standard. Many cryptographic libraries include test suites that automatically verify MGF1 implementation against RFC test vectors during development and continuous integration. This automated testing helps catch regressions and ensures that updates to the library do not accidentally break MGF1 functionality. MGF1 versus other expansion functions. MGF1 is not the only way to expand a short seed into a longer mask. There are other cryptographic expansion or derivation functions that serve similar purposes, and it's valuable to understand how MGF1 compares to these alternatives. This helps us appreciate why MGF1 was chosen for OAEP and understand when other functions might be more appropriate. One alternative is a key derivation function like HKDF, which stands for HMAC-based key derivation function. HKDF is designed to derive multiple keys from a single master secret. Like MGF1, HKDF can expand a short input into longer output. However, HKDF has a more complex structure with an extract phase and an expand phase, and it is designed for slightly different security properties related to key derivation rather than mask generation. HKDF would work as a mask generation function, but it is more complex than necessary for OAEP's needs. Another alternative is to use a stream cipher like CHA-20 or AES in counter mode. You could use the seed as the key, start with a 0 nonce, and generate as much keystream as you need for your mask. This would be fast and secure. However, stream ciphers weren't as widely standardized and analyzed in the 1990s when OAEP was being designed. Hash functions were well understood and universally available, making them a natural choice. Additionally, using hash functions for MGF1 means that OAEP only needs to assume the security of RSA and hash functions, rather than also requiring trust in a block cipher or stream cipher. A simpler alternative might be to just use the hash function directly without the counter mechanism. You could hash the seed, then hash the first hash output, then hash that result, creating a chain of hashes. This would work but has a disadvantage. Each hash output depends on the previous one, so the hashing operations must be sequential. With MGF1's counter approach, all the hash operations are independent and could theoretically be computed in parallel. On a multi-core processor, you could compute multiple hash iterations simultaneously. This parallelizability is a nice property even if most implementations don't take advantage of it. MGF1 represents a good balance of simplicity, security, and efficiency. It is simple enough to implement correctly in just a few lines of code. It has clear security properties based on well-understood hash function assumptions. And it is efficient, requiring only straightforward hash operations without complex state management. These qualities made it the right choice for PKCS number 1, and it remains the standard mask generation function used with RSA-OAEP today. While alternative expansion functions have been developed since then, MGF1 continues to be used because it works well, and changing it would break compatibility with existing systems. Common implementation mistakes. Even though MGF1 is a simple algorithm, there are several common mistakes that implementers make. Understanding these pitfalls helps you avoid them in your own code and helps you audit existing implementations for correctness. Let's walk through the most frequent errors and how to prevent them. The first common mistake is using the wrong byte order for the counter. The RFC specifies that the counter should be encoded as a 4-byte Big Endian integer. Big Endian means the most significant byte comes first. So, a counter value of 1 should be encoded as 0x00, 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 0x01. Some implementers accidentally use Little Endian encoding where a counter of 1 becomes 0x01, 0x00, 0x00, 0x00. This produces completely different hash inputs and therefore completely different outputs. The code might appear to work and generate random-looking masks, but it will not interoperate with standard implementations. Always verify your integer to bytes conversion is using Big Endian encoding. The second common mistake is incorrect truncation. After generating enough hash outputs, you need to truncate to exactly the requested length. Some implementations incorrectly round up to the nearest multiple of the hash length. For example, if 100 bytes are requested with SHA-256, they might return 128 bytes, which is 4 times 32. The calling code might not notice if it only uses the first 100 bytes anyway, but this is still incorrect according to the standard. The mask should be exactly the length requested, no more and no less. The third mistake is forgetting to initialize the counter at 0. The counter should start at 0 for the first iteration, not 1. This seems obvious, but it is an easy mistake to make. Starting at 1 means your first hash output is from seed concatenated with 0x, beginning with 00, ending with 01, instead of 0x, beginning with 00, ending with 00. This produces completely different masks that will not match standard implementations. The fourth mistake is using the wrong hash function or not allowing the hash function to be configurable. Some implementations hard-code SHA-1 because that was common in older code. But SHA-1 is now deprecated and should not be used. Your MGF1 implementation should support SHA-256 and other modern hash functions. Ideally, the hash function should be a parameter rather than hard-coded, giving flexibility to use different hashes as needed. The fifth mistake is not handling edge cases properly. What if the requested mask length is 0? What if it is larger than the maximum the counter can support? Good implementations validate inputs and handle edge cases gracefully. Zero-length output should probably just return an empty result. Very large lengths should either be supported or rejected with a clear error message. Testing your implementation with edge cases helps catch these issues before they cause problems in production. RFC 8017 Compliance and Standards. RFC 8017 is the authoritative standard for MGF1. This RFC, published in November 2016, superseded earlier RFC 3447 and defines PKCS No. 1 version 2.2, which includes the MGF1 specification in Appendix B.2. Understanding what the RFC says and how to ensure compliance is important for building interoperable cryptographic systems. The RFC defines MGF1 with mathematical precision. It uses specific notation where MGF1 is a function that takes two inputs: MGF_, which is an octet string of any length, and mask_len, which is a non-negative integer representing the desired mask length in octets. The function returns mask, which is an octet string of length mask_len, or it returns an error if mask_len is too large. The RFC specifies that mask_len should be at most 2 to the power of 32 times the hash length. The RFC describes the algorithm in terms of octet string operations. An octet string is just a sequence of bytes. The specification uses concatenation operations where the double vertical bar means concatenate octet strings, and I2OSP, which means integer to octet string primitive, for converting the counter to bytes. The RFC is very specific about this conversion. The counter is converted to a 4-octet string using big endian representation. This precision in the specification is what enables different implementations to interoperate. To be RFC compliant, your MGF1 implementation must follow these specifications exactly. You must support all the hash functions that the RFC mandates or recommends. You must use big endian encoding for the counter. You must truncate output to exactly the requested length. You should implement the error checking specified in the RFC, for example, rejecting mask lengths that are too large. You should support mask lengths from 0 up to the maximum supported by the 4-byte counter. Compliance testing involves verifying your implementation against the test vectors in the RFC appendices. The RFC provides several example computations showing specific seed values, mask lengths, and the resulting masks in hexadecimal. Your implementation should produce exactly these results. Additionally, interoperability testing with other implementations is valuable. If your implementation can generate masks that can be verified by OpenSSL's implementation, and vice versa, that is strong evidence of compliance. Many cryptographic libraries undergo formal certification processes like FIPS validation, which include verification of RFC compliance. If you are building security-critical systems, using certified libraries provides additional assurance that the implementations correctly follow the standards. MGF1 in other cryptographic schemes. While MGF1 is most commonly known for its use in RSAESOAEP, it appears in other cryptographic schemes as well. Understanding these other applications shows the versatility of MGF1 as a cryptographic building block and helps us appreciate its design. Let's explore some of these other uses. One important use is in RSA-PSS, which stands for RSA Probabilistic Signature Scheme. Like OAEP for encryption, PSS is a padding scheme for RSA but for signatures rather than encryption. PSS uses MGF1 in its padding generation to create randomized signatures. The process involves generating a mask from a salt value using MGF1, and this mask is used to obscure parts of the signature structure. This randomization makes RSA-PSS signatures more secure than older deterministic signature schemes. MGF1 also appears in some key derivation schemes. While dedicated KDFs like HKDF are more common today, some systems use MGF1 as part of their key derivation process. The idea is to take a master secret, run it through MGF1 to expand it, and then partition the output into multiple derived keys. This works because MGF1 produces a long pseudo-random output that can be split into independent-looking key material. In some custom cryptographic protocols, MGF1 is used as a general-purpose pseudo-random generator. For example, in systems that need to generate initialization vectors or nonces from a seed value, MGF1 provides a standardized way to do this. The deterministic property is valuable here because both parties in a protocol can independently generate the same IBS from the same seed, enabling synchronization without additional communication. MGF1 has even been proposed for use in post-quantum cryptography schemes. Some lattice-based encryption schemes need mask generation functions similar to what OAEP needs, and MGF1 is a natural choice because it is well studied and does not depend on classical hard problems that quantum computers might break. The hash-based structure of MGF1 is believed to be quantum resistant, making it suitable for future cryptographic systems. However, these are still research areas and have not been widely standardized yet. The main takeaway is that MGF1's simple and secure design makes it useful beyond just RSA-OAEP whenever you need to expand a short seed into a longer pseudo-random value in a standardized, secure way. MGF1 is a reasonable choice. Its presence in multiple standards and schemes demonstrates that the cryptographic community has confidence in its design. Practical guidelines for using MGF1. Let's wrap up with practical guidelines for developers who need to use MGF1 in their applications. These recommendations come from years of experience in the cryptographic community and help ensure you use MGF1 correctly and securely. First and most important, do not implement MGF1 yourself unless you are a cryptography expert, and your implementation will be reviewed by other experts. Use well-established cryptographic libraries like OpenSSL, Bouncy Castle, Python's cryptography library, or similar. These libraries have implementations that have been thoroughly tested, audited, and used in production by millions of users. They handle edge cases correctly, use efficient algorithms, and are maintained to fix any discovered issues. Rolling your own cryptography is dangerous because subtle implementation errors can completely break security. Second, always use modern hash functions. Use SHA-256 as a minimum, or SHA-384 or SHA-512 for higher security requirements. Never use SHA-1 or MD5 with MGF1, even for non-security critical applications, because using deprecated cryptographic primitives establishes bad habits and might lead to their use in security-critical contexts. The performance difference between SHA-256 and SHA-1 is negligible on modern hardware, so there's no reason to use the weaker function. Third, ensure your seeds are truly random. MGF1's security depends entirely on the seed being unpredictable. Use your operating system's cryptographic random number generator. /dev/urandom on Linux, cryptgen-random on Windows, or sec-random copy bytes on Mac OS. These are designed to provide cryptographically secure random data. Don't use language built-in random functions like Python's random module or C's rand function for generating seeds, as these are not cryptographically secure. Fourth, understand the context in which you're using MGF1. If you're implementing OAEP, make sure you understand the complete OAEP algorithm, not just the MGF1 component. MGF1 is just one piece of a larger system. Make sure you're using it correctly within that system, including proper label handling, message padding, and error checking. If you're using MGF1 for another purpose like key derivation, understand the security properties you need and verify that MGF1 provides them. Fifth, test thoroughly. Use the test vectors from RFC 8017 to verify your library is working correctly. Test with different seed lengths and mask lengths. Test edge cases like zero-length masks or very long masks. Test with different hash functions. Include MGF1 verification in your continuous integration testing so you catch any regressions or environment-specific issues. Finally, keep your cryptographic libraries updated. Security vulnerabilities are discovered over time, and library maintainers release patches. Staying current with updates ensures you benefit from security fixes and improvements. Set up automated dependency updates or at least regularly check for new versions of your cryptographic libraries. Conclusion and future of MGF1. We've covered MGF1 comprehensively, from its basic concept through implementation details to practical usage guidelines. Let's recap the key points and look at what the future holds for this important cryptographic building block. MGF1 is a beautifully simple solution to a common problem in cryptography: how to expand a short random seed into a longer pseudo-random mask. Through its use of a hash function with a counter, it achieves this expansion in a way that's secure, efficient, and verifiable. The elegance of MGF1 lies in its simplicity. The entire algorithm can be implemented in about 20 lines of code, yet it provides strong security properties based on well-understood hash function assumptions. This simplicity is a virtue in cryptography because simpler systems are easier to analyze, implement correctly, and verify for compliance. The deterministic nature of MGF1 makes it perfect for protocols where multiple parties need to compute the same masks independently. The flexibility to use any hash function and generate any length output makes it adaptable to different security requirements and use cases. MGF1 has proven its worth over more than 25 years of use in RSAE-SOAEP and RSA-PSS. It has been extensively analyzed by cryptographers, and no practical attacks have been found. It has been implemented in every major cryptographic library and has been used to protect countless encrypted messages and digital signatures. This track record gives us confidence in its continued use going forward. Looking to the future, MGF1 remains relevant even as cryptography evolves. While RSA itself may eventually be replaced by post-quantum algorithms, the general concept of mask generation functions will remain important. New cryptographic schemes often need similar expansion properties, and MGF1 provides a template for how to build such functions securely. The hash-based construction of MGF1 is believed to be quantum-resistant, meaning quantum computers don't provide any particular advantage in attacking MGF1 compared to classical computers. This makes MGF1 suitable for use in transitional cryptographic systems that need to bridge classical and post-quantum security. As hash functions continue to evolve, MGF1 can simply be used with newer, stronger hash functions. If SHA-3 becomes more widely adopted, MGF1 works just as well with SHA-3 as with SHA-2. If entirely new hash function families are developed, MGF1 can use those too. This future-proof design is another example of good cryptographic engineering. In conclusion, MGF1 exemplifies how good cryptographic design creates tools that remain useful for decades. Its combination of simplicity, security, and flexibility has made it an essential component of modern cryptography. Understanding MGF1 not only helps you use RSA-OAEP correctly but also provides insight into the principles of good cryptographic design that apply broadly across the field. Thank you for your attendance. Please consider subscribing to the